it's not your first math class, you know. It's always the careless errors. And they really got to come up with a better name for that. Because it's not like you didn't care when you made the error. You're not sitting there being like, who gives a crap? I'm not going to put the units. I'm not going to label this graph. It's like, crap, I forgot. A forgetfulness error. I don't know, it doesn't roll off the tongue quite the same way. A silly error. Nah, stupid error. Oh, I thought you said stupid error. I'm like, yeah, that works too, you know. Human error, yeah. So, outliers. Outliers are hugely important. All right, so this is the reverse of what I was just talking about, where I was saying that the mid-range is like one of those concepts where you don't want to throw away the point, but it's not the most like earth-shattering concept. But outliers are. It's like fundamental to statistics. If you identify outliers in a data set, they have to be handled appropriately. But the first step in doing so means that you have to identify the outliers, right? So you have to identify what value is so far off of what is appropriate within that data set that it sticks out like a sore thumb. Context is a good resource when it comes to that, because in a lot of cases you look at just the background. I know everybody loves word problems in math classes. It's just the way of it, you know. Like, forget the procedural stuff. Yeah, solve equations, x equals this. Oh, bring on those word problems. That's where it's at. I like to contextualize and visual. No, it's the opposite. But in this class, the word problems are going to help you get a leg up, because I might look at this data set and say, I don't know if there's an outlier there. I mean, the definition, any value that falls outside the range of blah. Look at that thing. Everything that we learn in this class will have a calculator shortcut, right? So this is no different. Nasty formula, I'm going to show you a much easier way to do it, but again, let's learn the ins and outs first, all right? So this problem has no context. Determine if the following set consists of any outliers. There's just some numbers there. I mean, the 42 is a lot bigger than the rest, but I don't know. If the context is, here's a set of values on the interval of 1 to 100, well, they're all appropriate, all right? But now throw a little context in there, all right? Students were selected randomly from a local elementary school, and their ages were listed below. Context. Like, I don't have to do any math now. That 42 shouldn't be there. I'm not even sure the 2 should be there. All right? I mean, you can make a case, I guess, for the 2 being there. Maybe it's bring your toddler to school day. I don't know. But the 42, I mean, it could be a Billy Madison sort of thing. That joke doesn't land as much anymore. Like, when I first started teaching, they're like, oh, Billy Madison, what a great movie. And then now it's like, oh, yeah, that's the one with, is that Ben Stiller in that? Or is that, okay, you know, good. So that's the thing, like people just don't know. They just don't know. Should watch that, though. It's a good movie. Happy Gilmore, obviously the better of the 2, right? We all agree on that, yeah. Right, so that's good. We're all on the same page here. Ace Ventura 2. The hands went down. That's crazy. Ace Ventura, awesome. Ace Ventura, I like. Ace Ventura 2, I think, aged better. Ace Ventura 1, I think it aged quicker.
The second one, When Nature Calls?
Yeah.
That was the one, right?
Yes, and I quote that every single day of my life. I quote it even when I don't think I'm quoting it. Shakaka. So, anyway. And I'll tell you, I can't walk past the canned tuna fish at Costco without saying, Bumblebee tuna? Bumblebee tuna. I can't say the rest of it. It's very inappropriate. Homework, watch any of the movies that I just said. Just do it, just so we could all be on the same page in terms of the movie quotes. I do like to drop the odd movie reference every once again. And I mean, it's not going to count for points or anything, but it does count for goodwill. I dropped a movie quote, you recognize what it is, I become happier. And then everybody ends up being happier for it. All right. So we know what the situation is. We suspect that the 42 is an outlier. We don't know why yet, or how, whichever word makes more sense. We have that formula, though. That formula is going to help us mathematically determine whether it is an outlier. Now, context always overrides the math. That's something that is going to be entirely frustrating in this course because it's a 4-credit math class. There's supposed to be math happening, like solve this equation, make that graph, label it, maybe make another graph just because your teacher told you to, and then solve another equation just for the hell of it, and do it all over again. It's going to be more like, here's a set of data. What's going on with it? Draw a conclusion from it. And within that process, you will do some math, you will create some graphs, but then you're also going to analyze the context behind that data. I try to keep the context as universal as possible. I try not to skew in any particular direction. I will say that sports lends itself very well to statistics because the data is published and easily accessible, and it's transparent. There's no hidden agendas there. I mean, there's hidden agendas everywhere, but if somebody rushed for 1,300 yards, they can't say, rush for 1,300 yards, but, he still sucks. Like, it's not what it is. It's 1,300 yards, and that's it. The individual ran for 1,300 yards. And then you make a determination of how that stands relative to the other individuals who rushed, whatever that means. So the sports works very well, but the thing is, what sport are you familiar with, if any, on an individual level? So I could put a football question on every single test. You're like, oh, crap. I know everything there is to know about soccer, but I don't know anything about football. Right? Well, soccer, football, it's always. Because they're like, well, football is soccer. I'm like, not that football. Soccer, football, baseball. I hate baseball. Okay, there goes that one. Lacrosse. What's that? Like all these different possibilities. So I try to keep it as user-friendly as possible. So, like, I like to ski. Now, you don't necessarily have to ski in order to understand that a person has got a couple of sticks on the bottom of their feet and they're using them to propel themselves down a mountain at unsafe speeds. All right? That is pretty much what's happening. Right? So I'll give you some times. Like it took this individual a minute and a half. It took this individual a minute and 45 seconds. And then you could say, well, I know less time to complete a trip means you got there faster. Right? You don't actually have to have been a skier in order to understand that. And you can fill in the blanks. Okay, he's saying skiing, but I'm seeing sleigh riding. Like whatever it is, just fill it in your mind. So, but the context will give you a sense of what's going on. So if this is the elementary school student, yeah, that 42 is not supposed to be there. Now, is it because there's a 42-year-old sitting in the class? Or is it because the individual who collected the data forgot to hit the tab after the 4? 2, tab, 4, tab, 5, tab, 6, tab, 7, tab, 8, tab, 9, tab, 10, tab, 42. I forgot to do the tab between the 4 and the 2. All right, so it's supposed to be a 4-year-old and a 2-year-old. If there was an element of human error involved where they displayed the data incorrectly, and that threw everything out of whack. Right? It's kind of like when some of you have never done this, but so I'll say the collective you write down a problem, but then because your handwriting is such trash, you misread your own handwriting and write something that's completely incorrect, even though your first step was fine. Like that 2 became a Z for some reason. It just slowly morphed itself into something else. It happens, So we'll get into how we handle this, but the context is going to determine whether or not that 42 stays in the data set or gets removed. We know it shouldn't be there, but honestly, if there really is a 42-year-old student enrolled in that class, then this data set is appropriate and that outlier should not be removed. If somebody forgot to hit the tab after the 4, then that's an incorrect data value, and it should either be corrected. Like if you can pinpoint and say, okay, they did not separate it, it's supposed to be a 4 and 2, you're absolutely sure that that's the case, then fix the data. If you're not, take it out, play it safe. All right. So how do you find the outliers? Well, we got to talk about these values. All right, we got an LQ. We got a UQ. And we have an IQR. The LQ is the lower quartile. Now, regardless of the fact that we're going to eventually learn how to do this stuff all on the calculator, you still want to know what each of these things represents, right? Just because it will play a role in how we do things. All right. That lower quartile can also be symbolized with a Q subscript of 1, which means the same thing as the first quartile, which is the same as the 25th percentile. All of which I'm going to write in a second, but I want to write the beginnings of the next one first. All right, so upper quartile because I don't want to scroll back and forth. So UQ is the upper quartile, also represented with a Q sub 3. The Q1 again represents the first quartile. The Q sub 3 represents the third quartile. The first quartile and the third quartile, you're thinking in terms of quarters. 1 quarter, 25%, 3 quarters, 75%. So 25th percentile, 75th percentile. All right, so a natural question would be, well, what about all the other percentiles? What about the 50th percentile? Well, we already have that. It's the halfway point. That would be the median. All right, so we already have that. The 0 percentile, that's the start point, and the 100th percentile would be the end point. All right, we don't need any of those values for what we're about to do here, but they're going to be useful down the line too. All right. The IQR is something called the interquartile range. All right, so interquartile range, and it's just the difference between Q1 and Q3. So you could say the difference between LQ and UQ, upper and lower quartile. Oh, sorry, I wrote it backwards. Like a friggin' noob here. This is crazy. Q3 minus Q1. It's the whole walking and chewing gum thing. So it's the difference between the upper and lower quartile. And so what it does is it gives you a sense of where the bulk of the data exists. Now, not only before this is all over with, are we going to learn about measures of center, mean, median, mode, and all that good stuff. We're also going to learn about measures of spread and variation. So how varied the data set is or are. All right. Because really, I think it's just important to know how spread out a data set is as it is to know what the central value is. I go back to my classic airport example because, and it's, I kind of refreshed it a little bit. It's not classic anymore. It's brought into the 21st century because I just got the TSA pre-check, and man, that's life changing. If you haven't done the TSA pre-check, please don't, because then you're going to be on the line too, and then it's like if everybody has TSA pre-check, then all the people that are on those line. What's that?
They have a third thing now.
Oh, like an upgrade. Oh, the world, the global
entry.
Yeah, I got to do that. I got to get the enhanced driver's license too. I'm ready to re-up on my driver's license. I want to get that bad boy. So I get lots going on in my brain right now. But the TSA pre-check thing, that was like just to reduce the variability, because back in the good old days, pre-check, it was like, I mean, you're going to JFK to fly somewhere. Depending on where you're going to go, it could be 5 minutes through security, or it could be 2 hours to get through security. I mean, it was like a complete crapshoot. So what do? You get to the airport 4 hours before your flight, and then you sit at the gate for 3 hours and 55 minutes. And you're like, this sucks, right? Or you're running late, or you just kind of roll the dice. Well, last time it took 2 hours to get through, so I'll do that. Or maybe you say, yeah, it can't possibly take 2 hours to get through. So you get there 2 hours before the flight and you miss your flight. I remember like 20 years ago, they used to go through the security line. They used to go through baggage drop-off and security lines. Okay, so the flight to Orlando's leaving in like an hour. If anybody's on that flight, come with me. You know, they're like, well, we'll get you on the flight. Like, you guys can wait because your flight isn't until this afternoon. Why you're here at 8 a.m. is on you. But like they would kind of get you through. Now it's like, oh, anybody here for Orlando? Yeah, your flight's leaving in 45 minutes. You're not making that. Go home. Catch the next one. You know, like they don't care anymore.
Quite 20 years ago, yeah. This was after 9/11.
Yeah.
Really.
That's when they start.
Just walk through with somebody.
Yeah. Well, that's the other thing. That's the other thing. I did not, and I still don't like it when they kind of mail it in on the security check. They're like, oh yeah, go. And it was funny because I forget which airport I was at. I think it was it was in Hawaii somewhere, where they're like, all right, we're getting backed up here. Yeah, just go. I'm like, whoa. Search that guy, and take me too. Like, you got to search somebody here. Come on, start doing the random checks. Let's do it.
My dad is always the one who gets picked for like the random spot check. Like everybody has to like the thorough.
Me too. I get it because I look suspicious.
He gets it because he's technically not a citizen of the United States.
And they just sniff that out.
Well, it's not his because he doesn't. Have
Oh, so that you mean he's randomly selected.
He lives here, but he has a permanent green card.
Right. But so when that comes through, when he goes through and talks to the guy, they're like, all right, have a nice day. Check that guy. So, yeah, that's the thing. But we reduce the variability by, making adjustments to plans. Like, I get the TSA pre-check, so my variability for security has been significantly reduced. I know that now, instead of having a window from 5 minutes to 2 hours of possible variability, it's now like 5 minutes to 25 minutes. So more predictable means that I can now plan accordingly, and that's a good thing. All right, so an interquartile range gives us a sense of the spread of the data. All right, so No, that's not what I wanted to do. All right, so it gives us a sense of the spread of the data. All right, so how do we find these things? Well, first we're going to identify the median. So we're going to count our way inward. Median is 7. And then we're going to find the median again, but this time for the lower half of the data set. All right, so I'm going to ignore that middle value, that median, and I'm going to basically treat the numbers 2 through 6. It's already in ascending order. I'm going to treat the numbers 2 through 6 as its own data set and find the median there. So smack dab in the middle between the 4 and the 5. So this would be my LQ, which is going to be 4.5. Then I'm going to find the median again. Starting on the high side of the 7, I have this set of values between the 8 and the 42. I'm going to treat that as its own data set and find the median of that set of values. So smack dab in the middle there would be 9.5. So 9.5. So there's my UQ. So LQ, UQ, Q1, Q3, it doesn't make a difference what you call it as long as you're reasonably consistent. So I'll say LQ, and I'll write that that's equal to Q1 again, is equal to 4.5. UQ is equal to Q3, which is 9.5. And IQR, Q3 minus Q1, which is going to be the difference between the two. And that's just going to be a clean 5. All right, so now it's what we do with that. All right, so our formula is bracket LQ minus 1.5 times the IQR, all of which we know, comma UQ plus 1.5 times the IQR. So 4.5 minus 1.5 times 5, comma, so it's two separate calculations, one giving us the low bound and one giving us the upper bound of what we're going to call the non-outlier interval. All right, so I'm looking at the UQ, which is 9.5 plus 1.5 times 5. And so, well, 1.5 times 5 is 7.5. So 4.5 minus 7.5 is -3. And 9.5 plus 7.5 is going to be 17. And so this is the interval of non-outliers. You could think of it as like the ordinary or expected values. The values that you would expect to see in the data set should be in this interval. Now, again, context is an overriding factor. Because if I told you that these are ages of elementary school students, and you saw an age of -3, you're going to think that there's something wrong, right? So the context tells you, all right, this says -3 to 17, but it can't be the negative values, can't be 0. It's got to be something bigger than 0. I suppose there could be an infant there. You know, like what is the additional context? Are these students at the elementary school, or are they just people who are physically in the class in the elementary school? In which case the 42 could be okay, right? But what we get from this is the conclusion mathematically that therefore, and if you didn't know, 3 dots in the form of a triangle means therefore 42 is an outlier. All right, and so in every single data set, we are going to check for the presence of outliers. Now, you look at this, there's a fair amount of notes here, and I kind of wrote big. So you'd look at it and say, oh, okay, what's the real amount of work that you did? It's really not that significant. But if I told you, bless you, that you had 13 problems to do and you had to identify outliers for each one of them using this approach, you drive yourself insane. So we definitely need a shorter way of doing this. Sorry. Question?
So you know 42 is the outlier because of the 17.
Right, because this is the interval of good values. Any value that does not fall between these two numbers is going to be an outlier. So any number in the original data set that's lower than the -3 or bigger than the 17 would be considered an outlier.
So those brackets, they matter?
They do, because that tells us that these values are included in the set of non-outliers. All right, so if 17 was in a data set, in the original data set, that would be okay. All right. 18 is the first, assuming that they're all whole numbers, 18 would be the first bad value. The first value would be considered an outlier. All right. So yeah, that's where we're going to leave it. All right. So big old display, yeah, 2.814, etc. Depending on the notation, some of this information may be necessary and some of it may be completely irrelevant. All right. So at least for now. I can tell you that before the course is over, we're going to use practically all of the information in this display. If you hit the down arrow, for me, I can just swipe. But if you hit the down arrow, then you could see that there's a lot more information. All right, min, Q1, MED, Q3, and max. Those correspond with the outlier values that we came up with last class. All right, so the calculator is going to give us all of that information. All right. I did mention, or at least I intended to, that the shortcut for coming up with outliers is involving data entry in the calculator, but it's a substantial shortcut, right? To the point where it'll just flat out do the work for you and just tell you what the outliers are. All right, so I can say that this is one technique that you could use to come up with those values, the interquartile range, and plug them into the formula, but I got something even easier for you. All right, so we'll just wait on that. All right, but at this moment, what we can say is that the X bar value, again, X bar is the way that we say the sample mean. We go to 3 significant digits, so in this case, that's about 2.815. Now, you saw the MED option as you scroll down. MED is 3. That's our median. All right, so it'll tell us the median also, which is great news. The only thing it's not going to tell us is the mode. All right, range and mid-range we can come up with just based off of this information as well. All right, so we get everything we need right out of this menu or display also. But like I said before, what I'm going to do is just show you very quickly how you would do it by hand. Again, it's not going to be a requirement, but it's worth taking note of the underlying theory, just because it's kind of nice to know how it's working, why it works the way it does, why you can't just add up the numbers 1 through 5 and divide by 5. That's kind of a biggie. All right, and it comes from the idea that the number 1 occurs 10 times. All right, so this is the number of times X occurs. All right, so that's what a frequency is defined as. The number of times the X value occurs. So I can't just say that the 1, like if I wanted to find the mean, the 1 happens once, the 2 happens once, the 3 happens once. The 1 is happening 10 times. So if I was finding the mean, I would have to say 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, 1, 1, 1, plus 2 plus 2 plus 2, 3 of those, plus 3, plus 8 of those 4s. I'd have to count them all off and add them all up. and then 5 of the 5s. Count them all off and add them all up. All right? As opposed to doing that, instead of adding 1 together 10 times, why not just multiply 1 by 10? So that would give me a product of 10. And by the same reasoning, 2 times 3 is 6, 3 times 1 is 3, 4 times 8 is 32, and 5 times 5 is 25. All right. Now, if I add these values up, I don't know that what we get will be surprising, but the one thing you might be surprised to find out is that it's actually on the list. That's over on the calculator on the right hand side. All right. 10 plus 6 is 16, plus 3 is 19, plus 32 is 51, plus 25 is going to be 76. All right. In our display, it says the sum of x, because remember that funky e means the sum. The sum of x is equal to 76. So what the calculator did was it actually did this behind the scenes. It wrote that number 1 out 10 times. It wrote that number 2 out 3 times, 3 out once, 4 out 8 times, and 5 out 5 times. Then it added them all up, came up with the 76. The n represents the sum of the f values, which is 27. So it actually did that for us. And then also behind the scenes, it determined what 76 divided by 27 was. All right, and that ended up being about 2.815. I tell my high school students this specifically because depending on the question, because they have to take a Regents exam, depending on the question, they may have to show the work. They may have to complete a table. And I'm like, you know what? You can kind of fake your way through the work because the calculator is doing the work for you. It's adding up your x values. It's counting up how many values are in the set. You just have to take the 76 and divide it by the 27. I'll like just write that down on paper and just write what the mean is, and you have it. And behind the scenes, they're actually learning something, which is kind of cool. All right, so that's one of my favorite things to do: trick people into learning. Doesn't always work. So that's the mean. Ultimately, you're just going to need to come up with the answer. It would also be nice if you learned the underlying concept. Right. So then the median. Well, there it is. It's 3. Yeah, that's all there is to it. You just look in your list, and there it is. But what has happened in the past, and you know, I'm doing the extra explanation on this one because people have walked away with the misconception. They would say, all right, median, middle number, got it. All right. Gonna count inward, just like you showed me. There it is, median 3. And just like that, it's the median is 3. So that must be how you do it. It's coincidental because what we're looking at is a relatively symmetric distribution here because we have 13 on one side and we have 13 on the other side. All right, on the low side and on the high side. All right, 13 values here, another 13 values there. If I counted all those 13 values from one end to the other and the other end back towards the first end, so both ends to the middle, I would get to that 3. As a result, that would be the single value, right? But that requires a graphical way of reasoning this out. So what I do instead is I actually say, why not write the number 1 out 10 times? The number 2 out 3 times. But that's not a 2. Those are not 2s. I got in a groove there. The 3 out once. The 4 out 8 times. That's reasonably visible. and then the 5 out 5 times. There's no way you're going to be able to see this one. So let me get one more in there. All right, so those are the actual values. If I listed them out, those are the numerical values. All right, so if I wanted to find the median for this, what I would have to do, just like we did last class, is just start counting our way towards the middle. 2, 3, 4, 5. And it doesn't take too long before you're like, what was that calculator approach again? How do you do that? Please teach that one again, because I like that. I don't want to do it this way. 1, 2. Just keeping on counting your way in the middle, or in towards the middle. All right, and then let's switch over to the green. 1, 2, 3. And then finally we get to the middle value, which is right there. There are 13 values on either side. Here's 13 values. 13 values. All right. Now, hey, it does beg the question. Maybe it doesn't. I don't know. I don't know how you are at begging questions, but something that I would be concerned about is, well, what if, let's say, for example, instead of this being a 5, what if that were like a 95? You know, like what impact would that have on the median? Right? What if it were a 0, meaning that the 5 didn't occur at all? Well, that's going to be an easier thing to consider, because if this last entry was 0, then none of these values occurred. Right? So this is the end of our data set. So then we start counting inward from that last 4. And so what that's going to do is it's going to shift our median a little bit more towards the 1 and 2s. All right? Whereas if I had more 5s, let's say I had 20 more 5s, what that would do is it would shift the median further down the line. All right? So the more values you have as extreme values, the more of an impact it has on the median. All right? So instead of actually doing that out by hand, a nice, easy way of doing it would be to just change your data a little bit and investigate. All right, so instead of making this last value 5, like I said, make it like, I'll make it really extreme. Make it like 95, and then recompute. So stat calc 1, and besides, the more you play around with it, the more familiar you become with the functionality, and the easier it becomes. L1. L2, so list L1, frequency list L2, and then go to calculate. You have that. Now, that's specific to mine. That's why I was saying it's a little bit of an issue. But all I care about is the median. I mean, the mean is a lot higher than it would have been, but the mean is higher. It's like 4.5. The median is 5. Right? That's telling us that the middle number in the data set is a 5. All right. And that's because I just added on 95 more 5s. So I have a total of 100 5s. If I started at that last 5 and with the 1 and started counting my way into the middle, I'm going to be squarely into the 5s, somewhere in the 50s before I got to that median. And so the median would be a 5. So it all depends on the distribution, but it's very easy to do on our calculators, and so that's really the moral of the story question.
The N stands for the sum of the frequencies?
Correct. All right, so I put the data set back to what it was originally, just so I can continue on with this. So stat calc, 1 variable stats. This is one thing that I think is particular to mine. See how it's putting it into the field there? If that ever happens, there are some functions on your calculators where if you if you don't quit out first before you start going on to the next function, it'll try to type that function in as an entry into the data. If you ever get into that jam, just quit, which is second mode, and it won't lock in that attempt, right? It'll revert to what it was prior to that, right? So then I can do my stat calc 1 and calculate, and so this is what the data should have been. And now I'm looking for the mode, all right? So you look down your list and you say, oh wait, there's no mode. Not there's no mode as in the answer is no mode. There's no mode as in it doesn't say mode here anywhere. All right, but then you think about the definition of the mode. All right, the mode is the most frequent value in a data set. So then you're kind of looking at it as like, wait a minute, do I even need a calculator for that? Which number occurred most frequently?
1.
1. All right, so the mode is 1. One occurs 10 times, everything else occurs less. I honestly have no idea if I'm spelling occurs right. It's one of those words that is not in my wheelhouse.
Just says it in a sentence.
That's disgraceful.
So frequency will
You spell it
always
right.
define-
All right. Say it again.
Frequency always define the mode?
Frequency is always going to give you the mode, yeah. So whatever the largest frequency value is, that's going to be your mode. Right? And there can be a tie. So if you have the largest number is 10, for example, but the 10 occurs maybe for the 5 also, then you would have 2 values that make up the mode. That's perfectly fine. In the case of something like this problem here, where the data is set up in interval form, it could be a little trickier. So what we do there is we call it the modal interval. So I'll actually start off with that because it's kind of fresh. So the modal interval would be the interval that has the most representation, so the most values in it, so 50 to 59. All right. And the one thing that you're going to start to, well, I'll say have to consider, but it's the kind of thing that you realize makes perfect sense once you think about it. And that is, like, it's not always about the center of the data, because, and I always default back to class averages, and it's all right to talk about in here because we haven't taken a test yet, so it's not a sore subject for anyone, all right? But if I tell you that the class average is an 80, you can say, okay, thanks for the information. If I tell you it's a 90, same thing, cool. Then you get your test back and it's a 60, and you say, what the hell? And they said the class average was a 90. And you say, well, it's an average. Not every value is going to be 90. So, I mean, not necessarily anyway. It is possible that every single person in the class got exactly a 90 on a test. I've never experienced that before. The closest I got was in, let's say it's 2009. Maybe it's 2011, but it was a long time ago. I was teaching an Algebra 2 honors class, and we were doing trig identities. It's trigonometry. And the test, I thought it was a reasonably challenging test, but apparently I'd given them so much practice with the concept that they had experienced every type of question that I could possibly ask. So when I gave them the test, they were done. It was a 40-minute test. They were done with it in like 15 minutes because they were just prepared. Nobody cheated. They were just prepared for every single question. They're like, I've seen this one before. I've seen that one before, whatever. Like I honestly, I gave them like 100 different examples to practice on and enough time to do it. And then I chose 6 out of those 100 and I gave them a test on it. And they all got 100s, except for one student who got an 80. It was the closest I got to a clean sweep. Now, an 80 is nothing to sneeze at, You know, in a math class, a difficult honors level math class, you get an 80 on a test. You know, I mean, my son came home with a 97 on a spelling test today. I thought my wife was going to kill him. So, I mean, everybody has different standards, but I mean, that's nothing to sneeze at. But then when you find out that the other 19 people in the class got 100s, you're like, oh, dang it, that was my chance, you know. So I think that person was kicking themselves. But that was the closest I got to what we call standard deviation of 0. All right, a standard deviation is just a measure of how spread out data are. If it's 0, it means all the data values are exactly the same. All right, it's very rare. It hardly ever happens. So if I tell you that the class average is 80, you should be like, all right, you've told me nothing. That's the answer. I have to tell you how spread out the data are. All right, and so that ties together with this concept because in this case where we had individual values that made up the classes, the frequency corresponded with an individual number. So 1 occurred 10 times. It's simple. 1 is the mode. I can't say that the mode is in the 50 to 59 interval, right? Because maybe those 92 values are spread out evenly among those 50 to 59 integers, all right? So there's 10 values to play with here. Maybe each one of them occurred roughly 9 times, all right? But then you get into this interval here, 20 to 29, maybe the number 21 occurred 13 times, all right? It's still in this interval that you have only 13 values, which is much less than this, but the mode would actually be in this interval because the number 21 occurred 13 times, whereas the number 51 occurred 9 times, 52 occurred 10 times, 53 occurred 8 times, you know, it balanced out to an average of 9.2. But you can't really tell from this. So instead of saying the mode, we say the modal interval. All right, I'll accept the mode interval, all right, just because there's things I'm willing to be nitpicky about, and then there's things that I'm like, I can't take off credit for that. They'll hate me for the rest of my life. You know, I am firmly, I figured, I've been teaching for 20 years. After I taught for like 5 or 6 years, I had taught well over like 2,000 students. So if I'm using that as a benchmark, I got to be in the 10,000 range at this point. There's got to be people that like hate my guts to the point where they wish me dead. And then there's got to be people that think I'm like the greatest person in the world. And then an overwhelming majority of people are like, I had a math teacher one time who's bald and he had a beard. I forget his name. You know, like it usually is like overwhelming quantity in the middle and then a couple of extremes. Right? I don't want people hating my guts. It's like fitting into that category because I took off half a point on their test for writing mode instead of modal. All right, so you don't have to worry about me nitpicking about that. In fact, I will tell you explicitly what I will be nitpicking about. All right, there will be no surprises on that. Hint, labeling graphs. You don't label your graphs, you're going to lose credit. I am extremely nitpicky about that. And in this class, that might be one of the only things I'm nitpicky about. All right, so everything else is just like, it's all negotiable. All right, so then the question would be, how do we come up with the mean and median? Well, you can't type an interval in our calculators. So what we do instead is we type in a value that is a good representative of that interval. The best way to do that is by finding what we call the class midpoint. All right, so find the midpoint of each interval. So what I'm going to do is I'm going to take 10, I'm going to add to it 19, and I'm going to divide by 2. So essentially I'm finding the mean of that interval. I'm averaging them together. So we're going to get 14.5. Poor quality 4, let me fix that. I'll write 0.5. I was about to write the fraction. Is this typo bonus coming in? What's this? I'm buzzing crazy like it. No. just people that don't understand that I am occupied. Do the same thing for 20 to 29. You don't have to show this work if you don't want to, especially once you realize that all you have to do is find the first entry and then add 10 consistently, because the next one's going to be 34.5, 44.5, and 54.5. So the first column, again, the X column goes into L1, and the F column, the frequency column, goes into L2. All right, so stat edit. Now to clear your data, all right, very important, because people want to hit delete to wipe out an entire column, and that ends poorly. You can overwrite the data. The problem is, if you just, for a previous problem, you typed in 30 pieces of data, and now you only need to do it for 5, that's a lot of deleting to have to do. What you do is you go right up to the column heading, so right on to L1, hit clear, don't hit delete, hit clear, and then enter. And it'll wipe out only the contents within that column, all right? If you hit delete, it'll wipe out the column itself, including the L1 heading. All right, and then before you know it, you run out of L's and game over. Nah, I just have to help you figure out. I have to help you get it back, and then train you to not do it again. All right, so right in the column heading, clear out, hit clear, and then enter. Alternatively, if you want, I'll just show you very quickly, and I'll write it on the sideboard here. If you hit second plus, and then I'm not sure if it's stat on your calculator. I'll just check real quick. Second plus option 4. You can wipe out all the lists in one shot, and it'll never mess with your L's. All right, so clear all lists. Use the function clear all lists. So second plus option 4. And then enter after you do that. All right. The obvious drawback to that approach is if you have 10 lists of data and you only want to get rid of one of them, if you select this function, you're going to get rid of 9 columns of data that you don't want to get rid of. So clear all lists, hit enter, it'll say done. You go back in, stat edit, you have a nice fresh blank slate to work with. More experience you get with this, the more you're going to realize that the only way you can screw this up is by typing the data in incorrectly. So take your time, double check it. I find that checking it in a way that's different from the way I typed it in is a way that is helpful for me. So I typed it in column by column, so I'll check it row by row. Just a thought, it works for me. It may not work for you, maybe it does, I don't know. Just when I'm giving these strategies, it's not so I can hear myself talk, it's because I've seen these errors so frequently over the years that, it's like, oh, I remember that one time this person did that, I was surprised, so let's try to avoid that. And it on and on and on. All right, so same process from here though, which is good. Little consistency. Stat calc option 1, L1, L2 for frequency list, and then go down to calculate and hit enter, and you get this outcome. Now again, we only needed the mean and median here because we already got the modal interval, and the calculator wasn't going to give us the mode anyway, so that part's taken care of. If you're familiar enough with the symbol, you don't have to label it. X bar, again, is the sample mean. In this unit, we're only working with samples, so you'll see that I labeled everything just the mean, but it is implied to be the sample mean. And that's approximately 38.511. And the oh, well, I was going to say standard deviation, but we don't want that. The median is 54.5. Now, the median is an estimate. All right. Well, actually, everything's an estimate, but the median is more of an estimate than everything else because that's relying on these 92 values all being 54.5. All right, each one of them. All right, but like I said before, if it's evenly distributed from the 50 to 59, that may not be the case. All right, and so something, and you really only, and it's kind of weird because this course is so jam-packed with content that we don't have time to explore the most basic thing that makes all this stuff work, and that is how the data are distributed. Really what we're looking at is the idea that if this is distributed evenly, so 9 values for 50, 51, 52, all the way up to 59, if we average those values together, we would get something in the neighborhood very close to 54.5, all right? But the median in this interval, so, I mean, that could be anything, right? So if it's evenly distributed, yeah, it could be 54.5, but if all of the values are 51, then the median is 51. If they're all 59, then the median is 59, right? If half of the values are 55 and the other half are 56, then the median is 55.5, right? Bless you. It all comes from exploring the data, but that's, I think, the class in and of itself. All right, so for now, we just learn the skill, and then we go from there. All right. So speaking of going from there, we have the concept called standard deviation. All right. Measures of variation. They fall into a bunch of different categories, but the important one is standard deviation. All right, that's what I was talking about before when I said, if I tell you that the class average on a test was 80, you say that's meaningless. And I say I agree because it doesn't tell you what you got on the individual level. It doesn't really tell us how the class did as a whole. All right. If I tell you that the mean is 50 and the measure of spread, which we're calling standard deviation, is 0, then you know what everybody got. Right? If I tell you that the class average is a 50, which is not good, but the standard deviation, the measure of how spread out the data are, was, let's say, also 50, then that tells us that the data is very widely spread out. On an individual level, that equals hope. Because if you studied for that test, you know you prepared, you're like, well, I'm gonna be a deviation from the mean on the high side, because I didn't find that test difficult at all. We've all walked out of the classroom, sometimes on the long end and sometimes on the short end, where people are like, that test was so freaking hard, and they're not even being that polite. And then other people are like, I don't know what you're talking about. It wasn't that bad. I thought it was easy. And you're like, you shut up. Just failed it. Studied all night. You know, it all kind of balances out in the end, because the next week you're on the opposite end of it, where you're like, oh, I got 100 on that one. Oh, you're not talking now, are you? You know, so, but it has to do with the standard deviation, because you don't know how everybody else compares to you with just the mean, all right? And you don't know how everybody compares to each other with just the mean, all right? So what we do is we figure out a number that represents the spread of the data, right? If that number is very small, if it's close to 0, it means the data is very tightly packed. If the standard deviation is very large, it means the data is more loosely organized. Right? So when I'm dealing with two separate sets of data, it's very easy to see which data set is more tightly organized and which one is more loosely organized. Right? Because one will have a smaller standard deviation than the other. All right? So that's kind of nice. The problem is one data set all by itself, you get a standard deviation, be like, I don't know, is this a good one or a bad one? Standard deviation is very comparative, right? It's not very meaningful unless you have something else to compare it to, right? Aside from the fact that smaller is better, right? Context is a very important driving factor behind a lot of this stuff because, like if you're talking about medicine, like if you work in medical research and you're trying to develop a new drug that will regulate I was going to say heart rate, but I'll keep it simple, blood pressure. Like you don't want a large variation. You want it to actually be able to do what you're saying it's going to do, right? So it's going to reduce your blood pressure by whatever, give or take. All right, that give or take is your standard deviation. All right, you want that give or take to be small. You want it to be very, very predictable. All right, that's the power of this particular idea. I mean, we can go a little bit more simplistic with, the classic examples are, like 10 bags of M&Ms are randomly selected and weighed. The stated weight by the company is that it should be this amount, but when you collect the data, the weights were this and that and the other thing. Is the company telling the truth or are they full of crap? That's fine too. There's a lot of value in that sort of thing, but that's just getting a quick look at it. It doesn't really get across the idea of the power of the concept. I do it with gas mileage. Right? It's probably kind of a little too nerdy, but I want to see what the variation is in my gas mileage based off of my driving. All right, so I'll fill up my tank and I'll collect the gas mileage after the next fill up, taking note of what the conditions were in which I was driving. All right, is it aggressive driving? Is it long driving? Is it commuting? Because the kids got hockey tournaments that are 3 hours away. That's highway. And I got to commute to work. What's the variation? I normally get around 32 miles per gallon, give or take. What's the give or take when I'm commuting, and what's the give or take when I'm long driving? All right? When I'm long driving, I can tell you, just based off of empirical evidence, data collected in the nerdiest fashion possible, that much. Yeah, it's 33 miles per gallon, give or take 0.25 mpg. All right, pretty spot on. Commute to work all over the place. And it's a function of whether I'm running late. That's exactly it. So the data was so inconsistent I couldn't draw any meaningful conclusions. But long driving, pretty spot on. All right? And so that becomes predictable. Like now you can start planning things. On a larger scale, now you can start thinking about, like, for example, if you're in the airline industry, if you know what the average fuel consumption is going to be, give or take, with a small give or take, now you can set the rates for the flights. So if you've seen flight costs become more consistent over the years, it's because and it is, believe it or not, it is more consistent. It's just consistently high. It is because they have a better handle on the fuel consumption now. All right. So how do you compute these things? And we have to start with a basic example, of course. All right. It starts with a formula, and that formula is not very complicated, although it looks like it's terribly complicated. X minus X bar is the fundamental component of it. Because if you're going to find a standard deviation, you're probably going to want to find a deviation to begin with. All right, so this is my deviation. Just that inner part of the function. Everything else we do here is for the purpose of standardizing it. All right. Now I have my list of x values. I'm going to need an x bar. It's a simple list of data. This one we're going to do by hand first. It's actually pretty easy to do this for a simple set of data. For a frequency table, it's a pain, so we'll do that all in the calculator. But we'll use the calculator to check this one too. All right. So to get my x bar, I want to take the sum. All right. So 5, 11, 14, 20, 28 it looks like. So x bar is going to be equal to 28 divided by the number of values in the data set. So 7 is equal to 4. So I now know my x bar value. Let me get a nice horizontal in here. I'm actually going to draw a column that contains only x bar. So I'm just going to rewrite the number 4 7 times. And the reality is this is the only time we're ever going to have to do standard deviation by hand. So just write the column with the 4s in it. Like, who cares? You're never going to have to do it again. I'm not even going to ask you to do it on a test or quiz. All right? It's more about evaluating what it means than anything else. So x minus poor quality x, undo, undo. X minus x bar, so now you have an x and an x bar that you can subtract. 2 minus 4, negative 2. Negative 1, positive 2. Negative 1 again. Positive 2 again. 4, and then finally negative 4. Next up is x minus x bar squared. The idea behind this is, I'll call it the zero-sum conundrum. That's not even remotely what it's called, but it sounds fancy, and so most people go with it. The idea behind that is you can't always get a true sense of the deviation, the accumulation of deviation, the cumulative deviation among the x values from the mean, because some of the values are positive and some of them are negatives, and some of the positives offset with some of the negatives. So you don't get a true sense of the deviation. So there's two ways to handle that. One way would be to just drop all the negatives, because the deviation is a distance. Another way to handle it would be to raise each of these values to an even power. All right? So this becomes more of a what came first, the chicken or the egg kind of paradox, because you don't necessarily know that squaring the values is the way to go until later in the course, where you find out that pretty much everything else, everything that comes after this in statistics is related to the standard deviation, which requires you to square the values. All right. So it actually turned out that all of the concepts that followed this kind of came first and helped us derive this method for standardizing those deviations. All right, so most people interpret that as, okay, so we just square it? Yes? Okay, that's what we'll do. A handful of people in the past have had the thought of like, well, can we just drop the negatives? And so the answer to that is because statistics won't work the way we want it to if we do that. So square them all, we drop the negatives. Unless you type it in the calculator incorrectly and don't really think about it, which happens more often than you would think. All right, so we have all those values, all positive. If you type this in your calculator, just be careful when you're doing something like negative 2 squared. You shouldn't need a calculator for, but sometimes the numbers you can get some funky decimals. And this is just, again, some of us are turning these calculators on for the first time ever today. If I typed in negative 2 squared and hit enter, it's going to tell me negative 4, which is incorrect. All right. Actually, it's correct based off what we typed in, this is saying -1 times 2 squared. All right. What you really mean is -2 in parentheses squared. All right, which is the positive force. So very, very subtle thing, but it could cause you to get an answer and not really know why you got that incorrect answer. All right. So the numerator is telling us to add up all those values. So the sum of x minus x bar squared. We're just adding those values up. That's all there is to it. In your calculator or in your head, it doesn't matter. We have 32, 46, it looks like. 10, 16, 5, 10, 14. Yeah, I think so. All right. Then the bottom says n minus 1. All right. N is the number of values in a data set. In this case, n is equal to 7. So my s squared, which is the variance, which is not the standard deviation, but you got to get that before you can get the standard deviation, is 46 divided by 7. Welcome to leave that in fraction form if you want, or you can put it in decimal form. If you want a more precise standard deviation, you're better off leaving it in fraction form, because the next step is to take the square root of that, because s, 7 minus 1, thank you. So that would be 46 over 6. No need to simplify, because we're going to get a decimal final answer anyway. So s is equal to the square root of the variance. Which is the square root of 46 over 6. And that's where we get our approximate value. All right, so the square root of 46 over 6. I'm talking about 2.769 roughly. All right. And so that's our standard deviation. Our sample standard deviation. Now, in the next unit, we'll learn about population standard deviation. The only difference in computation is that you don't subtract the 1 in the bottom. All right. That being said, the real difference is that there is no difference whatsoever, because we're going to do it all in the calculator from here on out. So let's type this data set in our calculators. First, to verify that we didn't just screw this up. Which really would be all your fault, because I screw stuff up all the time. But when 30 people let me do it, that really makes it on you. Nah, you got to watch me like a hawk sometimes. My classic story is, and it had to do with this concept, standard deviation. The second example, I chose to do it by hand one semester. I screwed up the mean. Made a slight error with the mean. So if you recall, that was the first step. So we got like 25 minutes into the solution of the problem, and then a student said, oh, actually it wasn't even a student raising their hand. I was like, hey, let's check it on the calculator. The answer was wrong. And I said, dang, the answer was wrong. Then a student throws up a hand and says, oh yeah, I noticed you screwed up the mean in like the first step. And I was like, you noticed that 25 minutes ago and you didn't say anything? What the hell, you know? And so there's a classic balancing act of like, well, you're like a teacher. I thought you like knew the answer and stuff. So it was usually like I figured I screwed up somewhere, so I wasn't going to say anything and look like a schlemiel. So, you know, it is what it is. But if you see anything, out of whack, like that -1. Personally, I'd rather take the hit when I make the mistake, because I like the big reveal of like, all right, now let's check our answer with the calculator. Enter. See, it's exactly the same, as opposed to enter. All right, where the hell did I go wrong? All right, let's stare at this for the next 20 minutes, you know? So please tell me if you see anything. All right? So I don't take it personally. After 20 years of teaching, it's not possible to take anything personally anymore. So anyway, stat calc, 1 var stats. Now, this did not have a frequency list. This was only data that we typed in L1. So you want to hit clear on frequency list. All right, you want to blank that out. And then hit calculate. All right, so again, we have a lot of funky looking stuff here. We computed X bar, we got 4. Yeah.
What are you putting in L1?
The 2363680. Yeah, no problem. All right. One thing I don't like about I mean, there's a lot of things I don't like about the calculator, but it's like a necessary evil because it does so much. That's the good outweighs the bad. It says SX here, and we denote standard deviation with an S. So you might be like, well, is that the same thing? Well, we know it's the same thing because look, we got the same value. But aside from that, all the calculator is saying is S with a subscript of X, X representing the X values that you typed in. So S for those X's. All right, so when you think about it like that, it might start to make a little bit more sense. This other one here, this little sigma, lowercase sigma, that means population standard deviation. That's the second unit. All right, so just think unit 1, unit 2. You don't have to worry about this one yet. In the second unit, you have to worry about this one. You don't have to worry about this one. It'll be the reverse in the second unit. All right, so it's just the S at this point. So instead of taking you through, and this is the last thing we'll do for tonight, and then you'll be off the hook. Find the sample variance and sample standard deviation for the following data set. So stat, edit, wipe out the data that you have here, clean slate protocol. Movie reference, anyone? Which one? Very good. Very good. All right, so we got 10, 20, 35, 41, 52, 11, 14, 1, 3, 8. Double checking this way, that away, backwards, forwards, upside down, left and right. Okay. You just got to double and triple check. I try to, on a test, if things are slightly off, because I'll tell you right now, and I will give you the breakdown for what's going to be on the test question by question. Question 1 will be creating a frequency histogram. Question 2 will be creating a box. You know, you'll get that list. One of the questions is going to say find the mean, median, and mode, range, mid-range, standard deviation, variance, and it's related to a data set. You type the data set in incorrectly, you get all of those wrong. If I can find your mistake, it won't cost you much. If I can't find your mistake, it's going to cost you the world. All right, because that's what it is. You know, like if it's only slightly off, I'll be like, all right, you typed in something, let me try to transpose a couple of values, maybe skip a value. I'll play around with it and see if I can come up with your numbers. But if I can't find your mistake, then there's really not much I can give you. All right, so that's how important this is. You've got to double, triple, quadruple check your work. All right. That being said, it's a whole lot better than having to do all this crap by hand. So always keep that in mind. Stat calc, 1 var stats. Now I have a frequency list. All right, so frequency list, L2, second 2. and then calculate. So they're asking us for two things, sample variance and sample standard deviation. The calculator is giving us one, but not the other. All right, so the SX value, or just the S, is about, I'm going to write the approximate value here, but I'm going to caution you that in order to find, so this is a standard deviation, so S. In order to find the variance, we need to square this number, but you can't square the rounded value. All right, you have to square the more exact value, which means you need this whole shebang here. All right, I'll show you two ways to do it. One way is easier than the other. All right, so one way to do it would be to find the variance from the standard deviation. You just write that number down, the whole thing in its full glory, 16.230879, and so on. 25657. Then square it. All right. If you've already lost interest in that approach, I understand that. Some of us are like, well, simple and direct. It's not ideal, but I'm going to do it.
My calculator. Yeah, stops at 6.
Oh, okay.
Like the 2.6.
Okay. Yeah, that's fine.
2.5.
That's fine, because I make answer keys with a variety of different calculators, so I'll do it with your calculator, everybody's calculator, and it'll all work out. All right. The other approach, okay, so you can type that in and square it. Last I checked for some of these calculators, the minute you start typing in, it blanks out the screen. So make sure you write it down first. Otherwise, you have to recompute, which is not a big deal. All right. Now, an alternative. And since you will have a note card for the first test, and most people choose, that note card is 3 inches by 5 inches. You can't fit the entire unit on that note card, but what most people choose to do is put little calculator reminders on that note card. This might be one of them. SX, you can call that up in your home screen by going into the VARs menu. So I'll write that down. So VARs for variables. On your calculators, it's option 5 for statistics. And then you'll see the entry. It should be option 3. To call up the SX.
So it's
It's VARs, then option 5, which is statistics, and then option 3 is the one that says SX. And so that'll bring that right into your home screen. And so all you would have to do, so that brings SX into your home screen. All you have to do is square that number. And it'll compute it for you with the most unrounded form of that value. All right. So
it doesn't matter, because mine was off by like 2 digits.
yeah, it won't matter because it's in the calculator. It's stored the true value. It doesn't always display the same value between my calculator, your calculator, somebody else's, but stored within the calculator is a true value. And so then once we get this, we can round it to approximately 263.441. Now, you may get lucky. It happens sometimes. Maybe happens in this case. Let me try it with the rounded value, 231 squared. Oops, 16.231 squared. It may give you the same rounded. You see, it's a little bit off. And I always think stats, like we're the grunts. The statisticians are the people behind the scenes. We're not decision makers with the data. We're just doing the math for the people who are making decisions. All right. So I don't know what this data is for. I don't know if that deviation from 0.441 to 0.445 is a big deal. So if somebody asks me to run the numbers on something, I'm going to give them the most accurate possible value. All right. So this value is more accurate than what I would get if I just squared that number. All right. So we use the true value. Now, if you take this whole shebiggity bang here and square it, you should get this one rounded. All right. If you don't, then definitely var is 5, 3. Question.
So when we get to bars 5, 3, what do we do after that, for the SX?
So you call up that SX. So you're in your home screen. So vars. So you hit option 5 and then option 3. Then you hit the power of 2. So you're squaring it. So you're hitting this key. And then hit enter. And then it'll actually square your SX value. So it's a little recall feature. I mean, it's the closest the calculator has to copy paste.
Does it matter if you use the caret instead?
Yeah, oh, it doesn't matter. No.
263 is the variance.
263.441 is the variance, yeah. All right, and so you'll see on the test that there'll be a problem that says find the standard deviation and then find the variance. And so you're going to want to do it this way. You know, for us, it's a matter of, you know, losing half a point if you screw it up. But in the real world, it could be more devastating. I'll give examples of that next class. Question?
And what's the significance of the variance again?
The significance of the variance is just another measure of variation. So it goes hand in hand with standard deviation. There are other statistical techniques that we're going to learn later in the course that actually relies on variance as opposed to standard deviation. But it still just gives a measure of how spread out the data are. And just like standard deviation, it's a comparative measure. The bigger the number, the more spread out the data are. The smaller, the closer to 0, the more tightly grouped the data are. All right. All right, so that's where we're going to leave it for tonight. If you have any questions, stick around. Otherwise, have a wonderful evening, and I'll see you on Thursday. If you missed attendance, make sure you